So far, most of our time in physics has been spent studying something called kinematics. And kinematics is how we describe the way that things move. Now what we want to move into is something called dynamics. And in dynamics, we want to describe how forces impact motion. And to do this, we need to know what this word actually means. What is this word force? So what is a force? In its simplest sense, we can imagine that a force is just a push or a pull. That is a basic operational definition of a force. And it has both a magnitude and a direction, so we know forces have to be vectors. And what we can do when we're talking about forces is we can draw pictures of them, draw these force vectors, and when we combine all the force vectors that are acting in a system, we get something called a free body diagram. So let's show you what a free body diagram looks like. You draw kind of a coordinate axis first, so that you know what you're referencing with respect to. And then we can draw a couple of forces. Let's say I have one force F1 going kind of off in this direction, and I have another force F2 kind of going the opposite direction. Let's say both have the same angle from their respective x-axes. Both of these are theta. What I can do is I can imagine adding these together and getting a third vector that's the combination of the two. That F total equals F1 plus F2. We want to make sure that we denote that all of these are vectors, so they should all have little arrows right above their notation. So what do we do with this? Well, we do the same thing we always do. We break this into x and y components. So we have a little bit of force 1 going in the x direction and a little bit of force 1 going in the y direction. And we can break those up. And we have the same thing with force 2. A little bit of force 2 going in the negative x direction and a little bit of force 2 going in the positive y direction. And we can see from these that the force 2 in the x is going to cancel with the force 1 in the x because they're going in opposite directions, and we're left with only a total force going entirely up. So we can apply standard vector operations to our forces to combine them. And while all types of forces are vectors, there's two general categories we can put them into. We have contact forces, where your forces actually need to touch. And then the other type of force we have are called field forces. These don't require physical contact. So some examples of this. Let's say I have a box sitting on a table. So I'm going to draw a table. There's my box. And I have some forces acting on this. I have one force that's pulling it down. What's keeping this box on the table? Well, basically it's weight, which we can also call W, the weight, which is also the force of gravity. So I'm going to call this F sub g. This is gravity pulling it down. Now gravity is caused by the Earth and the Earth's mass. The Earth is not literally reaching up and pulling down. There is no contact here. So this gravity is an example of a non-contact force. It's a field force. Then we also have a force due to this table pushing up on this box, kind of holding it there. Right? The box doesn't fall through the table. We'll call this C, and we'll say that this is the contact force. It'll have another name we'll learn about called the normal force. And it is contact between the floor and the box. So the floor is pushing up on this box. So we've established now that all forces are vectors and that there's two types. They can be contact forces or field forces. Other kinds of interesting and important things that we need to know about forces, we need to know the units of force. And the units of force are named after the guy that we credit with their kind of discovery, the guy that kind of formalized dynamics, Isaac Newton. So the units of force we call the Newton. Very famous physicist. You might have seen the myths about him discovering gravity because of an apple. But that's not all he did. We can credit Isaac Newton with you actually having to take this course because he invented calculus. And he actually did that while he was on house arrest due to the Black Plague. And the Newton has a very specific definition. We define 1 Newton as the force needed to accelerate a mass of 1 kilogram at 1 meter per second squared. And it turns out that an apple, a typical sized, medium-sized apple, is about 1 Newton in weight. We've mentioned this already, but since forces are vectors, we have to treat them like vectors. We have to use all the rules of vector addition. So let's do an example. Let's say I have a force F1 that's equal to 5 newtons in the I hat direction. And then I have a force F2. F2 we're going to say is equal to 10 newtons in the J hat direction. And I want the total force between these. F total has got to be equal to F1 vector plus F2 vector. Depending on what I'm asked, I could write this in vector notation. Just write out the equation. F total is going to be equal to 5 newtons in the I hat plus 10 newtons in the J hat. This is going to be vector notation. And that's fine. Right? We're not implying that you need to add the I and the J components together because we have left this little vector symbol in there. Now, what if we ask you something more complicated? What if we asked you what's the magnitude of the total force? So we can draw our force out. We can make our little free body diagram and see what these forces are doing and see what this total force actually looks like. I have some force going in the x direction, so that's going to be my F1. That is equal to 5 newtons in the I hat. And then I have some other force, F2, that's going to be equal to 10 newtons in the J hat. So that's going to be going up. We'll say F2 is equal to 10 newtons in the J hat direction. Now the total force is going to be the hypotenuse of this triangle. So if I want to find the magnitude and direction of this, I have to do that using my standard vector processes. I have to put in an angle. We'll call the angle from the x-axis theta, and I can find the magnitude by using the Pythagorean theorem. So F total is going to be equal to the square root of the sum of the squares. So that's the square root of 5 newtons in the I hat quantity squared plus 10 newtons in the J hat quantity squared. So let's multiply this out, and we're going to find F total is equal to the square root of 25 newtons squared plus 100 newtons squared. So we'll take this square root and we'll find that F total is equal to about 11 newtons. And how do we find the direction? The direction, we use this triangle again. We use this theta. So this theta is my angle of interest. I can solve this any way that I want. I've been tending to use the tangent. It doesn't matter what trig function you use. You can use any of them. But I'm just going to go with tangent because I've been sticking with that more or less this whole semester. So we've got tangent of theta is F2 divided by F1, which we should be able to see in this triangle by now. We've done this stuff with vectors pretty exhaustively by this point. So theta is equal to the inverse tangent of F2 over F1. And theta is equal to the arctangent now, where we plug in our numbers of 10 divided by 5. So the arctangent of 2, and this gives me theta is equal to 63.4 degrees. And we need to specify where that is. That's going to be above the positive x-axis, which we can see from this picture that we've drawn. I've got my positive x-axis going along this way, and I'm going above that by some angle theta. And that's how we would add vectors and give potentially 3 different kinds of answers. In vector notation, we just write out the vector, making sure to include these unit vectors for specifying directions. Or if we're asked for magnitude, we can use the Pythagorean theorem. Or if we're asked for direction, we can find the angle using trigonometry.